I'm going to be presenting some material from my kind of the first chapter of my dissertation here at UC Santa Cruz. And I actually did this project largely based on data collected at Henry Cowell. So that's, I suppose, one of the reasons why I am speaking with you all today. But yeah, basically my talk is about the legacy of historical land use as recorded in the rivers of the Santa Cruz Mountains. And in particular, I'm going to be looking at the San Lorenzo River. Okay, so I just wanted to start off with this historic lithograph here of Santa Cruz, which was made in 1870. And of course, this is some time ago, but you can already see some familiar features, including downtown Santa Cruz, the wharf, the outlet of the San Lorenzo, and even Neary Lagoon on the left side. And then just for reference, here's the present day locations of UCSC as well as Henry Cowell State Park off in the distance. But, you know, as much as we can see some similarities here, there's one pretty noteworthy difference that's captured in this lithograph compared to today, and that's that there are no trees. So this is because, as most of you likely know better than I do, much of the Santa Cruz Mountains were logged, and we can see a pretty clear effect that had on the landscape. It's pretty barren. And so as it turns out, logging activities also have an effect on rivers. And that's kind of the main thing that I want to focus on today. Really, I'm going to be thinking about how the San Lorenzo River was affected by this. So before we get into that, I need to introduce some fundamental kind of pieces of information about why rivers are interesting and generally how they work. So, oops, go. Oh, there we go. So yeah, I mean, we all know pretty well that our lives and infrastructure are really inextricably linked to rivers. I mean, we rely on rivers for all sorts of things, including transportation, electricity, shipping, drinking water, and, you know, a lot of other things as well. And we've built our civilization completely around rivers, which means we've also modified them a lot for our own purposes. And meanwhile, while we're manipulating rivers in all sorts of ways, rivers are themselves incredibly dynamic and very responsive features of Earth's surface. So the shape and the position of rivers is constantly changing. And this is primarily due to kind of regular flooding and deposition of sediment over time. And so this image here that I'm showing is a map of the Mississippi River made using LiDAR imagery. So it basically sees through vegetation to the bare surface of the Earth. And you can see tons of these sorts of arcing shapes next to the present day Mississippi River. And those are basically showing previous locations of the river bends. So we can get a very good sense from just this image that rivers are constantly changing over time and are really, really kind of dynamic features of Earth. And I'm just showing another one because these images are amazing. But these come from I think an illustrator, a scientific illustrator out of Washington State, Dan Coe. Lots of really cool stuff on his website if you want to check it out. But this is all just to show that rivers are constantly evolving, and this is one of the most interesting things about them. And they change on their own, but they're also very responsive to particular human activities, and that's kind of what I want to focus on today. But we need to think about what ultimately determines river shape and behavior. Why are they behaving the way they do? Okay, so basically river morphology, which is just the kind of, you know, fancy word for the shape of the river, meaning its width, the depth, slope, how sinuous it is, that reflects this delicate balance between the sediment load that a river carries and the water that is conveyed within the river channel. And this is shown in this diagram here pretty well, which is a pretty famous diagram. This is an adaptation of it from Emery Lane that was made in 1955. And this illustrates that balance that I was talking about. So on one side of the scale, you have the sediment supply. So basically how much sediment is given to the river to move from the surrounding landscape. But on the other side, you have the transport capacity. So the ability of the river to actually move that sediment. So that's balanced with the sediment supply because, of course, the river has to move the sediment that's actually going into it, right? And so if we shift that balance between the sediment and our actual ability to move it, or in other words, the water in the river, that's going to tip that scale in one direction or the other. And we see this arrow in the center here that will point to either degradation or aggradation. That's basically a product of this balance here. So let's imagine we suddenly add a lot of water to the river, but keep the amount of sediment the exact same. That will end up tipping the scale to the right, and then we end up having this arrow flip to the left side pointing toward the degradation, meaning we're actually going to start eroding the bottom of the river because you're not providing enough sediment for the river to transport. Conversely, if we added more sediment than the river can actually carry, then the scale kind of tips to the left and we go to aggradation, or basically sediment deposition. So if you have more sand than the river can transport, you're going to accumulate sand within the channel. So yeah, basically depending on the balance between sediment supply and transport capacity, this can produce all sorts of different types of rivers. And within that sort of sediment supply and transport capacity, we also have things like the size of the grains, the slope of the river channel, is it steep or is it relatively flat? And so I'm not going to spend too much time on this diagram, but this is really just to show you that there's a whole variety of river forms that all depend on that balance between sediment supply and the transport capacity, or the river's ability to move sediment. So we have, some rivers that are really nice, like meandering rivers, and others that are more kind of clogged with sediment, and they tend to be this sort of braided system, like you can see on the bottom left. And in other cases, you have these kind of cascades with really large boulders and a lot of other things. So there's a lot of different types of rivers, and they're very responsive to these changes in sediment and water. Okay, so yeah, we've established now that rivers are really responsive to these changes in sediment supply and transport capacity. And oftentimes, any changes in that balance can be completely natural. This happens over long time periods as climate changes, for example. But often it's due to human activity as well. So this is what we're going to be focusing on today. And just to kind of start off with a fairly extreme example, we're first going to chat about the Elwha River, which is located on the Olympic Peninsula in Washington. And this river saw the largest dam removal in US history between 2011 and 2012 when the dam was taken out. And there were actually two dams, the Elwha Dam up to the north, and then the Glines Canyon Dam a bit south of there, and both had dammed lakes behind them. And these are shown in that map on the right there. And so over the lifespan of these dams, sediment had basically been accumulating behind them. And so when the dams were finally removed, that let out a ton of sediment that had been stored, and that was finally released downstream. And this is kind of shown in these images here of the Glines Canyon Dam. Panel A shows the intact dam. We move to panel B, and suddenly the dam's taken out, water starts pouring over the edge. Panel C, you can see that the river has now started carving into the sediment that was trapped behind that dam. And now we have a bit of a gorge forming. And meanwhile, you're evacuating all of the sediment from that system. And so by the final panel in the bottom right, the river has removed a bunch of sediment as it kind of cut downward. And so now all of that sediment is traveling downstream. And so just another vantage point, this is the partially drained lake upstream of the dam. And so this gives a really good sense of how much sediment is behind there. It's an entire field of sediment, basically. And so this sudden influx of sediment had a really big impact on the river channel itself. So these images are from downstream of the dam, right below. And as the sediment was reintroduced to the river, it ended up changing from a more kind of clear, meandering pool riffle channel. So you have little pools and more kind of spotty, what are called riffles, to something closer to what we see on the right, which is more of kind of a braided river with much larger, more prominent sediment bars. So there's been a lot more sediment deposition than there had previously been, which causes pretty clear and distinctive changes in the river morphology. So this isn't so relevant to my talk, but I had to include it. Not only did the dam removal change the river itself, but it also changed the coastline at this location, because the huge quantities of sediment leaving the system ended up building out this delta out into the Pacific Ocean, as you can see here on the bottom. So this is just one example of how rivers can dramatically change in response to shifts in the balance of sediment supply and transport capacity. And so in this case, that's due to human interference in particular. Okay, so now that we have a bit more understanding about how rivers evolve and respond to human activity, let's head back to Santa Cruz area and think a bit more about this landscape, which I showed at the beginning of the talk. Okay. So yeah, here in the Santa Cruz Mountains, we have a more local example of a river that seems to be affected somehow by past human land use changes. And that's the San Lorenzo River shown on the left here. And this was taken from the bridge going over the river at the Highway 9 entrance to Henry Cowell. And just to orient ourselves, this is the map of the San Lorenzo River. And here are some familiar locations with Santa Cruz, UCSC, Felton, Henry Cowell, and Boulder Creek labeled. And that entire kind of light shaded area represents the San Lorenzo watershed. So every droplet of water that lands there is flowing out through downtown Santa Cruz. But in particular, we're going to be focusing on Henry Cowell, where, again, that photo was taken. Okay. So this is an image of northern Henry Cowell State Park from Google Earth. Just to get us oriented, we have the park entrance on the upper left on at least the Highway 9 side and Felton. And then the visitor center in Redwood Grove on the bottom right there. And then we have Highway 9 labeled, as well as the San Lorenzo River labeled as the orange and white lines, respectively. And I also want to draw your attention to the area in the center of the image where I have floodplain in all caps. This is a this is a very broad, flat surface that's directly adjacent to the center of directly adjacent to the San Lorenzo River. And typically, we would interpret this sort of surface as the river floodplain, and so I've labeled it as such here. But there is one problem with this floodplain. Typically, rivers are expected to overtop their banks onto their floodplain every 1 or 2 years. But the San Lorenzo certainly doesn't flood that surface that frequently. It's only overtopped its banks like a few times in recent memory. So that's kind of not exactly with what we would expect based on what a floodplain actually is. So why is this the case? Well, if we've walked along the trails along the river, and especially this northern part of the park, you might have noticed that the river seems pretty far below the path. And so that immediately kind of makes you think, perhaps it's possible that the river can't flood because the channel is simply too deep, and maybe unnaturally so. So just to kind of help visualize that, on the bottom here is a picture I took of one location along the river near the Highway 9 entrance. And you have the trail and the floodplain up on the upper left where those people are standing. And then the San Lorenzo River is off to the right. And then I've basically taken that kind of red dashed line from the bottom and translated it up to be this sort of simplified cross section. And those two dashed red lines are roughly corresponding with each other. And so in this location, the riverbed is actually something like 6 meters or so, or 20 feet below the floodplain surface, which certainly seems very deep for the size of the river. And this could explain why the river no longer inundates its floodplain every year or two. And so, of course, this is still sort of anecdotal at this point. I haven't actually proven anything, but it's certainly possible that we're looking at a situation where the river cut downward or incised, as you can see in this diagram. So on the top here, we have kind of a normal, happy river, but then on the bottom, that river carves downward and the channel is deepened. So this situation might be what we're seeing in Henry Cowell State Park. So if we start with the assumption that there could have been recent incision in this area, the next question then is what caused it? Is it human land use or is it something else? So as I mentioned earlier, at the very top of the presentation, there have certainly been some pretty big disturbances in the San Lorenzo watershed, and the most significant one in the more recent history is clear cutting of redwoods. And so again, that was really clear in that lithograph we checked out with the fairly treeless landscape. But just to kind of drill that in, here's a map on the right that comes from a master's thesis from UCSC, actually. Rude published it in 1975. And every single one of these symbols represents a logging mill that was active at some point between 1842 and 1975 in the San Lorenzo watershed. And so, I mean, the main takeaway here is just that there was a lot of logging in the watershed, because it's a lot of points. And so that's the main thing there. But one particularly puzzling thing, some of you might know that typically when you cut down trees in a watershed, a common response is that more sediment actually erodes off the landscape and enters the stream, which causes the stream bed to build up sediment or erode. And that's the opposite of what I'm proposing. And so this might be similar to the Elwha River example, in which we introduced a lot of new sediment to the system and the river accumulated sediment in its channel. But again, let's go back to this diagram. So rivers will build up or lose sediment depending on that balance of sediment supply and transport capacity. So even if you do add a bunch of extra sediment into the river due to the tree removal, you might actually be able to counteract that with some kind of increased transport capacity on the other side of the scale. So in other words, you could kind of tip the scales in the other direction. So if you add more sand on one side, you just got to put more water on the other side. And this would cause the river to carve away at its bottom and basically cut downward. Okay, so indeed, there were some logging practices that were widespread in California that had the potential to degrade river channels and possibly overcome that additional sediment that was entering the stream. So again, these are practices, not necessarily just the removal of trees in general. And I'll describe each one of these that we're thinking about. First of all, because rivers were often used as major conduits for transporting harvested logs downstream to ports and ship them off to various places, often they would remove any kind of natural wood in the channel, like what we see on the upper left. This is a log jam in a river. So because those would be natural obstructions to sending logs downstream, they would take those out. However, if you do that, that actually reduces friction and turbulence of the water in the channel. So it's actually a lot easier to strip sediment away from the river bottom. So you're basically creating little dams here and there when you have logs in the stream just sitting there. And that actually allows sediment to kind of have little places to build up and prevent the river from carving away at its bottom. So that can actually protect the channel from incision. So if you remove that, then the river might be a bit more susceptible to down cutting. There's also this other practice that was common throughout the United States it was called splash damming. And basically it's where you build up large temporary dams. This is shown in the bottom here. This is splash damming in Pennsylvania. But yeah, so you build up a large temporary dam and then pile harvested logs behind the dam. And then after some time, you let water accumulate, and then the dams were blown up and logs were sent downstream in huge catastrophic log drives. And you can imagine that might have some kind of erosional potential on the bottom of the streams. And then finally, loggers also skidded harvested logs directly in the channel at low flow, which would kind of directly scrape away at the channel bottom and could also cause some amount of erosion. So it's not clear which of these methods or others were used in the San Lorenzo watershed specifically. It could be any of these, all of them or none of them. But we do know from other studies that all of these methods were employed actually 30 miles north of here in Pescadero Creek, in that watershed. That's from this really interesting report from Balance Geo in 2015. And they noted that all of these different logging practices contributed to a considerable amount of incision in Pescadero Creek. So we do have some kind of precedent. And again, we know that there was logging in the San Lorenzo watershed, so there's definitely some connection that we might be able to make between our Pescadero example and Santa Cruz. The same types of logging methods were likely present in both places. Okay, so onto a bit more kind of like methodological part of this talk. I really want to quantify exactly how much the San Lorenzo River incised or cut down. I also want to figure out when that happened, and then maybe with those two things in mind, we can confirm whether it was logging or something else that we haven't considered. Okay, so let's start off with how much has the river incised? Well, we don't really know what the San Lorenzo looked like before incision, in that kind of natural condition, but we have some kind of suspicion that the river cut down recently, so we want to confirm whether this happened and by how much. And so the strategy here is pretty simple. If we can predict how deep the San Lorenzo River channel should be in some natural state, based on the kind of present day water and sediment in the river, we can compare that to what the river actually looks like today. And if there's any difference between how deep we predict the river to be and how deep it actually is, that difference is going to tell us how much the river actually cut down. And so I'm going to walk through two different methods that we used for predicting a natural channel depth. And the first is this idea of kind of how mobile sediment is. And then the second one is an idea of formative discharge, or basically kind of the flood that shapes the river. So let's just focus on the first for now. This relates to basically sediment transport. And this theory states that the shape of a river channel meaning its depth and width, as shown here in this little diagram, those are going to adjust in order to move the sediment that's actually being carried by the river. So according to this concept, the river channel is going to be, it will evolve to be just deep enough so that when that channel is completely filled with water, the water exerts just enough stress on the riverbed to start moving sediment. So if we follow that line of thinking, we can actually calculate, there are various ways of calculating sediment mobility in kind of geomorphology, but just we can talk about this later too, but basically if you measure average grain sizes, you measure the slope of the river, you measure rock density, you can get a sense of how much water you need to move certain grains. And so we found that the expected flow depth of that type of river, based on the present day sediment sizes and water in the channel and the slope of the river, we expect the river to be about 2 meters deep. And that would reflect the kind of predicted depth of the river in natural state. So then the second idea is based on the fact that different sized flows in a river transport different amounts of sediment. So your everyday flow, for example, like you can see on the upper right here, that's a really common flood, but that doesn't actually transport that much sediment, right? It's low flow, that happens all the time, but there isn't actually that much sediment being transported. Conversely, if we look at the bottom, this is an image of the floods that we experienced this past year. That's the exact flip side, where you have an extremely infrequent flood event. It doesn't happen that often at all, but when it does, it transports a ton of sediment. And so this means there's some kind of optimization point between like small floods that happen all the time but don't transport that much sediment, and massive floods that don't happen very often but transport a ton. And that optimization point is basically the flow that transports the most amount of sediment if you consider kind of averaging across all of time. And we generally refer to this as the formative discharge. And so the thinking goes that this is the most influential type of flood for setting the geometry of rivers. So the depth of that formative flood, that kind of the flood that transports the most amount of sediment over time, that depth should be the depth of a natural channel, according to this theory. So we gathered a bunch of flow records and sediment data from the gauge at the Highway 9 bridge. And after considering the frequency of the different flow events and the amount of sediment that was transported at every single kind of flood stage, we were able to find some kind of optimal sediment transport point, and that's the formative discharge. And this flow depth was essentially somewhere around 3 to 4 meters, which is basically another estimate of that kind of expected channel depth of the San Lorenzo River. So now let's compare these estimates to the actual river channel. And so here's a cross-sectional view of the channel looking south from the kind of near the bridge coming off of Highway 9 again. And the floodplain is shown on the left. That's where the trail is. And then this dashed line represents basically the flood level if we filled the channel completely with water. And then each of these two gray regions at the bottom, those show the range of depths that were predicted by those two different theories I discussed. So the sediment mobility theory predicts the channel should be about 2 meters deep. And then the formative discharge theory says that the channel should be somewhere around 3 to 4 meters deep. And we can compare these to the actual depth needed to fill the channel, which is around 6 meters. So the difference between the sediment mobility theory and the actual depth is somewhere around 3 to 4 meters. And then the other difference is around 2 to 3 meters. So we're estimating that the river is probably incised somewhere between 2 to 4 meters because there's at least 2 to 4 meters difference between our expected depths and the actual depth of the channel. So that's pretty considerable. So we're thinking that there have been at least 2 to 4 meters of incision here, somewhere around 6 to 13 feet. Okay, just as a brief aside here, this incision and effectively the abandonment of that floodplain, because it no longer floods, as at least every year or two, has real non-academic significance as well from both kind of a natural hazard standpoint as well as an ecology perspective. So if a river channel is too deep for the river to flood onto its floodplain, on the one hand, it does decrease flood risks, but on the other, it makes the river a lot faster and more erosive. So you end up with major erosion problems sometimes and bank destabilization, as shown in this this image here from Seattle. Well, somewhere outside of Seattle. The news station is in Seattle. Anyway, so in addition to that, floodplains are really diverse ecosystems that provide habitat for a number of aquatic and terrestrial species. And so, for example, salmon and trout species like the steelhead that are shown here, they rely on floodplains for spawning, actually. And the fact that the degradation of river channels throughout California, the degradation of river channels throughout California, is one reason for the decline of a lot of these fish populations. So this is all just to say that river incision is a very real issue and important for multiple reasons. Okay, so just to go back to the motivating questions, we've now answered this first question: how much does the San Lorenzo River cut down? We're thinking it's somewhere around 2 to 4 meters. So now that we know how much the river cut downward, we want to know when that actually happened. And that may help us confirm when or whether logging is responsible or if it's something else. Okay, so normally, as I said, rivers flood onto their floodplains periodically. But when they do that, they often also deposit sediment next to their channels, so onto the floodplain. And so if we can figure out the age of some of those sediments that were deposited on the floodplain over time when it was regularly flooding, then that might tell us when the river was not yet incised, because it was still connected to its floodplain. Fortunately, there's a lot of charcoal actually in the floodplain sediments, the kind of sands and silts, and we can use those little bits of charcoal for radiocarbon dating. So with some help from some folks down at the U.S. Geological Survey in Santa Cruz, we went up to y'all's neck of the woods and extracted a sediment core from the San Lorenzo floodplain right next to the river, permitted, of course, as shown in this image on the right here. And then I picked out some charcoal from the sediment core and sent the samples in for radiocarbon dating. And so I got 10 different radiocarbon dates from the floodplain sediments. And so this here is a chart showing all of those radiocarbon dates from the charcoal samples. And they're organized by depth on the y-axis there. So every single sample is ordered from the kind of the shallowest sites at the top down to the deepest sites in the core. And then time is on the x-axis. So we have time moving forward to the right. So the present day is on the right side of the plot there. And then every single date is shown by some of these basically little green bracketed areas. And basically these dates are represented as probability distributions rather than single exact dates, just based on the nature of carbon dating. And so basically we have some kind of like 95% confidence that the age of that sample is within that little bracketed area. So if you haven't worked with probability distributions before, they're basically like kind of smoothed out histograms where the taller peak in the green represents a more likely scenario, or a more likely age. So there's a lot of scatter here, but the important thing to remember is that each one of these samples basically represents a date when the floodplain was still active and the river was still regularly flooding. So this basically means that we're looking for the most recent date to give us a sense of when the river actually incised. So that means we should look to the right side of the plot and see that the latest dates are sometime in the kind of 17th to 19th centuries or so. Oops. So we can confidently say now that the floodplain was active until at least the right side of this plot in the 1600s and possibly until the 1800s. And any incision of the channel would have had to occur sometime after that, because that's the last time that we see any evidence of a connection between the floodplain and kind of consistent deposition of sediment and the river. And just one quick note here, these dates, these final dates on the right side occur almost right before logging began in the mid 1800s. And those are shown as this gray bar here. The lighter gray just represents logging happening at all, and the darker gray represents a very intensive period of logging where they were employing kind of the most destructive logging strategies. So I'll come back to this in a second, but I just want to kind of draw your attention to that in the meantime. Okay, so we can now answer the second question: when was the floodplain actually abandoned? We know that there was 2 to 4 meters of incision, and that probably occurred sometime in the last 200 to 400 years. And it seems to coincide with a period of logging. And so maybe that could be the cause. It seems like we're sort of building some evidence here. So we know the magnitude and the timing of incision, and we suspect it could be related to logging. And the timing certainly makes sense, as we saw from those radiocarbon dates, with kind of logging as the culprit. But is there any other evidence for logging as a driver of incision here? Well, as I mentioned earlier, we do have that local example of incision that was driven by specific logging practices. So again, 30 miles north of here in Pescadero, there was splash damming, wood removal, dragging logs through the river channel, and all of those things caused the creek to incise dramatically. And so it seems reasonable to expect maybe the same thing happened here. And that's certainly the simplest explanation. But there are also other clues that we could look for to answer this question about logging practices and incision. And Specifically, we can look at the tributaries flowing into the San Lorenzo River, those small streams. And this is because we expect a lot of the logging techniques that I mentioned to be mostly present in the main stem river, so just the San Lorenzo River, because that was probably the main artery for transporting logs downstream. And many of the smaller tributaries, on the other hand, the little creeks that are flowing into the San Lorenzo River, those are probably too small to move a lot of the logs, especially the massive old growth redwoods. So that means that we'd probably expect incision primarily in the San Lorenzo River channel and less incision, or maybe none at all, in some of the smaller tributaries. So we can test this out. So I went out to Henry Cowell and just kind of kicked around in the river for a little bit. And there are several small creeks that are flowing into the San Lorenzo in this area. And this is a map here with the main river as the white stripe kind of zigzagging through the center. And a few of the tributaries are labeled here. And then the USGS gauge across the bridge at the Highway 9 entrance near Felton is labeled on the north, as well as our coring site. And I want to draw your attention also to the kind of broad colored regions in the map, which basically indicate ancient abandoned floodplain surfaces. So the river had different floodplains at different points in time, and over geologic time has been cutting down. Not so much in spurts of like 200 years or so. So in particular, the green kind of swath there is the floodplain that we're thinking about, the one that's more recently been abandoned. Anyway, so I went to look at each one of these labeled creeks, and I was hoping to get some more clues about incision and whether that occurred just in the San Lorenzo or if it also occurred in some of these smaller streams. So when I looked at some of these tributaries, I noticed that a few of them were actually overhanging the San Lorenzo River. So there was essentially little waterfalls above the main channel. And interestingly, the height of the drop from this kind of white dashed line in these images, so yeah, just to kind of like orient, the white dashed line, like here-ish, that's basically like me outlining the tributary channel, and then the blue dashed line shows where the drop is down to the San Lorenzo River. And so interestingly, the height of the drop from that white line down to the San Lorenzo ranged from about 2 to 4 meters above the channel, which again corresponds strangely well to the amount of incision that we predicted earlier. And so that suggests that, yes, indeed, incision probably started on the main channel, the San Lorenzo River first, and then didn't occur at all on some of these smaller tributaries. And this left those little tributary mouths kind of hanging above the San Lorenzo River. And so just to bring everything together, the timing of the incision from our radiocarbon dates, the nearby example of logging-driven incision in Pescadero Creek, and then these hanging tributaries all suggest that it's probably specific logging practices that drove incision on the San Lorenzo River. Okay, so just kind of the main takeaways here. The two different estimates of equilibrium channel depth suggest that there have probably been around 2 to 4 meters of recent incision on the San Lorenzo River. Then the radiocarbon dates of charcoal indicate that incision occurred sometime after the 1600s, possibly after 1800. And the timing of that, as well as some other things that we've looked at, suggest that it's probably logging practices that are the main, most likely drivers of incision of the San Lorenzo River. So just kind of projecting forward, we know the river incised, so now what? Is there anything we can or should do about this? Well, it's not exactly clear whether it's super easy to undo the incision when it's this extreme. And not to mention, nowadays there's development along the river and people probably wouldn't want flood frequency to increase. So if we're thinking about improving floodplain habitat for species like trout and salmon, as I mentioned before, restoration back to that original floodplain seems a little bit challenging for both like logistical and political reasons. So on the bright side, there are actually some locations along the river there where there seems to be some kind of new floodplain forming at a lower elevation. So in that diagram that I showed earlier, which is right here, there's this kind of lower bench directly adjacent to the San Lorenzo River between the trail and the river itself, that's basically eroding back into that abandoned upper floodplain. And in fact, this river is roughly in line with where we would expect the riverbank to be based on those two methods that I mentioned of predicting channel depth. So it's possible that given a few more decades, this surface is actually going to expand further and become kind of the new floodplain of the San Lorenzo River, which can provide new habitat for a lot of different species, which is pretty cool. Sort of all things return to equilibrium, I guess. So anyway, that's most of it. If you're interested and want to read more about this kind of stuff in detail, I published a paper about this last year in Earth Surface Processes and Landforms, which is a kind of rivery landscape geomorphology journal, and you can check it out here. But with that, that's all I have. Yeah, I'm excited to hear some questions and also some insight that I'm sure you guys have that you could add to this project as well. So thanks a lot.